Hello, my name is Kevin. Today's topic of conversation in the power engineering field is selecting a contactor. So let's discuss and make sure that we actually know what a contactor is. So a contactor is an electrically controlled switch used for switching an electrical power circuit. A contactor is typically controlled by a circuit which has a much lower voltage level than the switch level. So in other words, we could have a 12 or a 24 volt coil operating on a 230, 400, 525 volt network. Having a control voltage such as 110 volt means that it's much safer on the control voltage side while switching a much higher type of voltage. There are two main types of contactors, I suppose we could say. The one is an electrical hold type. In this case, the moment you take off the electrical energy to the coil, the unit will drop out. And the electrical latching type, which is you give a signal voltage and it latches in and stays locked in until such time as you give it another pulse. It's not that simple to just go along and choose any old contactor. We have to approach this with a bit of care, but it's certainly not rocket scientists, and we're going to go through that process, and I'm sure you'll come out with a lot of knowledge if you don't have that already. So you get different types of pole configurations. We could say a one-pole contactor, two-pole, three-pole, four-pole, and those poles could be normally closed or normally open. In the power industry side, we generally have things like a three-phase, three-pole contactor, and they are normally open if there's power not provided to the coil, and you provide coil, they switch in. Of course, there are specialist type of contactors, and we'll call those relays. These are generally in the switching level of things, not so much in the power consumption area. They are there to generate signals on and off, switching and closing contacts to make a process operate. You do get coils in AC types and DC types. So you could have a AC contactor running with a DC backup. Obviously, DC these days is catching on quite a lot of things, and you might have a DC control circuit. You can, of course, then switch AC and DC through the main contacts. And you get many adaptations to the overloads, additions like overloads, timers, you get different bases, and you get little relays. I mean, the relays could be PC board mounted even. There's a whole range of type of relays out there. So there's no fit and form in a specific industry like the electrical heavy current area. They might look a certain way. In the electronics industry, they look quite different. So here's two photos. On the right is your more traditional type of relay in a power industry. 3 poles, 3 normally open poles. You can see on the side here, you can get the status of this device by having auxiliaries in, and very important to actually make the relay hold in on a stop-start circuit, you need an auxiliary on the side. The left-hand one is far more complex, and you can see that this is a more relay type of arrangement. Lots more contacts, lots more arrangement that can be done to actually give signals when required in the status of things. Now, contactors, when you rate them, you need to know what they're going to switch. You need to know the frequency of that switch, and you need to know a certain amount about a contactor. So there's things like duty cycles, which are apparent to a relay or a contactor. 100% duty means, will they carry the rating forever, or will it just switch, click, click? And so you don't have to worry too much about what the switch was. It's not going to be a long time on or off. We have a whole range of things, and I haven't gone into the details here, but you get AC1, AC2, AC3, AC4. You get DC1, DC2, DC3, you get AC11, AC15, the contacts. So we need to just understand that for basic purposes, and we're talking more in the power industry here, AC1 is a resistive type switching load. That is a resistor type arrangement in the sense of there's no motor inrush. It's a standard, there's no real switching, heavy duty type switching. It's normally things like a geyser element, something like that, which is purely sort of a resistive in nature. AC2 slip ring motors, we don't really get too many of those, very specialist possibly. AC3 is again one of the most popular categories we get, and these are squirrel cage switchings on and off. AC4 is for the same thing, the squirrel cage motors, but this is inching and switching, heavy duty, severely duty, the type of thing like a crane gantry or something where you go stop, start, stop, start, stop, start to get 6 inches, you've done 15 operational switchings on and off. And you can imagine the inrushes to cope with that. Other portions to have a look at, or other typical things we need to have a look at, type 1, type 2 coordination. These may in fact be prescribed from a manufacturer. That's not today's topic, so we won't dwell too much on that. So what do we need then to select our contactor? We need to know the system voltage. So we need to be able to know this is going to go on 400 volt. We have to select a contactor that is capable of working at 400 volt. As I said, some of the very small relays and that may not be capable of that, or 525 or even 1000 volt. We need to know the control voltage. There's a coil involved, so we need to know whether we're AC and at what voltage it is, so that we size it there. If you put too high a voltage on a coil, you will burn the coil, obviously. We need to know the load size. We need to know what kilowatt that motor is, what full load current it is, the load type. It's a squirrel cage motor, for instance. Operational frequency. Now, this becomes important because contactors, the power type contactors in any case, are rated for things like 1 million operations or 3 million operations or whatever. So if we're going to do literally thousands of switchings per shift, we need to know how that is going to impact on the life of that contactor. And then the contact break medium, of course, most of the contactors out there will break in an air break, they're just a normal state, but you do get some specialist types, which we'll go into a little bit later. So environment for maintenance and care of these things, we need to have an environment which is dry and clean. It should not have fumes, it should not have moisture, and that type of thing will lead to a shortened and very much shortened lifespan. Contactors which are buzzing, or which have a severe buzzing as opposed to a coil frequency type buzz, might indicate that you have some sort of dirt or some piece of, I don't know, insulation maybe, stuck between the pole faces. They shouldn't generally have a very pronounced buzz. So look out for those type of things. You can open them. You can have a look at the contact wear and with a view to replacing or cleaning them. Most contactors in the power side are made to be opened and inspected. Again, if you damage a coil or you want to change the voltage of your control, you can generally replace the coils. Most manufacturers sell, specifically on the higher range of things, they'll sell coils which you can then self-replace. Generally speaking, lifespan prediction, notwithstanding the 1 million operations or 3 million operations, look at around a 10-year life cycle. If that is switching a process plant regularly, you probably need to look at that and say, plan on around about a 10-year replacement. So let's have a look at certain other types of contactors. Of course, we alluded that we've got air brake types. You also get vacuum type brakes. The contacts actually break in a vacuum. They're specialist type of tubes with the contacts in. They offer a much cleaner brake. There's almost no spark. It's a vacuum, obviously, so there's no oxygen in there to generate any oxides on the contacts. Vacuum tubes have a defined life. They're not the cheapest things around. There's not many manufacturers in the world that actually make the tubes, and many of the contactor guys use all the same manufacturers of the vacuum tubes. You can replace them. It's normally recommended to probably replace all three together if they've been generally used over a long period of time. They often have some form of counter on that, so you can determine that. Large contactors up to 11 kV might easily do, 250,000 operations, and good manufacturers might get 3 to 4 times the life of that. But you need to have a look at that process to see whether that's there. Typically, most of these would be used on fairly large motors, and the contacts last quite a long time under those vacuums. Now, contactors could, of course, easily just determine the workhorse of the electrical industry. These devices go out there and just work for a living. They work for many, many years until such time as they stop working. So contactors are the workhorses of industry, the electrical industry, and without them, probably nothing would in fact happen in our daily life. Everything that's controlled out there, everything that we probably use and we get from any process industry, bottling industry, canning industry, and anything that uses electricity has a lot of contactors in a processing plant. Without them, as I said, we would be surely, that whole process would stand. They are sort of really the workhorses of our industry. If you have any further inquiries or queries on this type of subject, please drop me a line and try to get back to you.